In section 5.2, we're going to talk about the characteristic equation for a matrix, okay? So we're talking about eigenvalues and eigenvectors, so we're continuing along those lines. So let's first start with an example of a matrix, and then we'll tie that into where we're headed with characteristic equations. So if I have a matrix A, 3, 0 on the top row and 2, 1 in the second row, so 2 by 2 matrix, okay? This is a triangular matrix. We can see that it's a lower triangular, okay? Has entries on the diagonal and only zeros above the diagonal. But for any triangular matrix, remember, we can simply read off the eigenvalues off the main diagonal, in this case 3 and 1. So those are our eigenvalues. Now I want to find out the corresponding eigenvectors. So I'm going to do A minus I. Remember, it's A minus 1 times I, the identity. Okay, so I subtract 1 from the entries on the diagonal, so I get 2, 0, and 2, 0 for my two rows, okay, which will quickly row reduce to 1, 0, 0, 0. Okay, which means then that I have a solution set where x1 is equal to 0 and x2 is a free variable. So the corresponding vector would be 0, 1. Okay, and then I know the other eigenvalue is 3i. There's 3, so I'm going to do A minus 3i. That's going to give me 0. 3 minus 3 is 0. 0 stays the same. 2, and then 1 minus 3 is a negative 2. Right? I can scale that and interchange those rows. And so I'm going to get 1, negative 1, and then 0, 0 for the second row, which I can see then we'll have x1 equal to x2, because again, we're going to move that variable over to the other side of the equation. Remember, we're setting these equal to 0 and looking for non-trivial solutions. And x2 will be equal to x2. So as a vector, then my vector is 1, 1. Okay, and then I could write the two eigenspaces. E1 would be equal to the span of the vector 0, 1. And E3, for an eigenvalue of 3, would be equal to the span of 1, 1. And there I have my two eigenspaces. I have a basis for them. Okay, I have all the information I need about that matrix. Okay. Now, as I look at this matrix, we know that we need the columns to be dependent in order to have an eigenvector, right? We have to have those dependent columns. So the original matrix A does not have has two independent columns. So that means that lambda equals 0 is not an eigenvalue. Okay. Remember that theorem applies there, or that idea. Okay. So I can find what I need to know. I need these dependent columns. So if I need dependent columns, I know that to have dependent columns, I need the determinant to be 0. Okay, so if I get a determinant of 0, that means I have dependent columns. We know that from the invertible matrix theorem. And remember, eigenvalues and eigenvectors, we're only talking about square matrices anyway, so we don't have to worry about putting that condition on there in the invertible matrix theorem. Okay, so a determinant has to be 0. Okay, well, what I'm looking for then is where the determinant of A minus lambda times I is equal to 0. Okay? The values of lambda, if I can make a nice lambda today, that satisfy the equation are the eigenvalues. Okay, so if I look back at my matrix A here, my matrix A was 3, 0, and 2, 1 for the rows. If I then go to A minus lambda I, I'm going to get 3 minus lambda and 1 minus lambda on the diagonal. My other locations stay the same, 0 and 2. Okay, and if I take the determinant of this matrix, I'm going to multiply on the diagonal, so I'm going to do 3 minus lambda times 1 minus lambda, and then minus the multiplication on the off diagonal, so minus 0. 0 times 2 is 0. And I'm setting this equal to 0. And so here again, we have 3 minus lambda and 1 minus lambda equals 0. So this must mean lambda is 3 and 1, which is exactly what we found before. Okay? So this mechanism is called the characteristic equation. Okay, the characteristic equation of matrix A is the determinant of A minus lambda times I equals 0. And the solutions to the characteristic equation are the eigenvalues. And once you know the eigenvalues, you can find the eigenvectors, similar to what we've done to this point already. Okay? All right, so let's look at a couple more examples here. Let's use the characteristic equation now to find our information about a matrix. So my new matrix A here is going to be 2, 3, 3, and negative 6. Okay, you see my matrix A there. So I'm going to take A minus lambda I then. That's going to be 2 minus lambda and minus 6 minus lambda. And the off diagonal stays the same, 3 and 3. And now I'm going to take the determinant of that. So the determinant of A minus lambda I multiply on the diagonal, so I'm going to have 2 minus lambda times negative 6 minus lambda minus 3 times 3 is 9. Okay, so let's multiply this out. So I'm going to get, and remember we're setting this equal to 0, okay, because that is the characteristic equation, is that equal to 0. So I multiply here, I'm going to have negative 12, first outside, inside last. So the outside is minus 2 lambda plus 6 lambda on the inside plus lambda squared minus 9 is equal to 0. Okay, so we keep multiplying, keep factoring here. So I'm going to have lambda squared in the front. 6 lambda and 2 lambda, negative 2 lambda go together to make 4 lambda. And then negative 12 and negative 9 makes a negative 21. And now apply your favorite factoring technique, right? I'm looking for two numbers that multiply to be negative 21, but add up to a positive 4. So that's going to be plus 7 and minus 3. Because 7 times 3 is 21. One's positive, one negative, so it's negative. And then 7 minus 3 is a positive 4. So this means that my eigenvalues, lambda, are equal to 3 and negative 7. So for a 2 by 2 matrix, it's pretty straightforward to solve the characteristic equation. You just get a quadratic, okay? You should be very familiar with solving quadratic equations. That's something you've seen in algebra and calculus and all along the way. Okay, so 3 and negative 7 are my eigenvalues, and if I needed to find the eigenvectors, I would find A minus 3i and A plus 7i, and I would row reduce those, and I would find the solution set, and that would give me the vectors that correspond to those eigenvalues. Okay, so my eigenvalues are 3 and negative 7. All right, let's look at another of that type, and then we will expand just a little bit. Okay, so my matrix A is going to be 8, 2, 3, 3. So again, I'm going to do A minus lambda I. I'm going to have 8 minus lambda and 3 minus lambda, and keep the off diagonal the same, 2 and 3. I'm going to take the determinant of A minus lambda I. That's going to give me 8 minus lambda times 3 minus lambda minus 3 times 2 is 6. And again, we are setting that equal to 0 for the characteristic equation. Multiply that out, so I'm going to have 24 minus 8 lambda minus 3 lambda plus lambda squared minus 6 equals 0. Continue to simplify, so I'm going to have lambda squared minus 11 lambda, and then 24 minus 6 is 18, equals 0. Now we need to factor. I have lambda and lambda, two numbers that multiply to 18 but add up to negative 11. Okay, 6 and 3 don't add up to 11. 18 and 1 don't add up to 11, but 9 and 2 add up to 11. And I need them to be the same sign, so both negative. So that'll multiply to a positive 18, but negative 9 and negative 2 add up to a negative 11. So my eigenvalues lambda are 2 and 9, using the zero factor property. Lambda minus 2 equals 0, so you move the 2 to the other side. And lambda minus 9 equals 0, so you move the 9 to the other side. So lambda equals 2 and 9 are my eigenvalues. Okay? Now for this one, let's keep going. So I'm going to do a minus 2i. Okay, so go back to your original a. So you're going to have 6, 2, 3, and 1. All right, let me get the camera to play nice there. 6, 2, 3, and 1. That's going to row reduce. Okay. I'll do it kind of slowly here. So I'm going to divide the top row by 2. So I get 3, 1, and 3, 1. Row reduce that again. So I'm going to get 3, 1, 0, and 0. Okay, so if you want to go fully, you divide that by 3, you get 1, 1/3, 0, and 0. Which would mean that x1 is equal to negative 1/3 x2, and x2 would be equal to just x2. Okay, but we like to get rid of fractions, so pick 3 for x2, so it will cancel with that negative 1/3 there, and leave me with negative 1 for the first term there. Okay, so you can see the negative 1 and 3 actually. If you didn't do that last row reduction step, you can see it here in that setup, right? Okay, so negative 1, 3 then is my eigenvector. You could also use negative 1/3 and 1. That's a fine eigenvector as well. Okay. All right, next we're going to go to a minus 9i, because that's my other eigenvalue. So 8 minus 9 is a negative 1. 2 stays the same, 3 stays the same. And 3 minus 9 is a negative 6. So same type of relationship here. I'm going to have negative 1, 2, 0, and 0. I can clear out that bottom row pretty quickly. And I'm going to wind up with 1, 2, 0, 1, negative 2, 0, and 0. So x1 would be equal to 2x2, and x2 would be x2. And so the eigenvector then would be 2, 1. So I have two eigenspaces. I have E2, which would be equal to the span negative 1, 3. And I have E9, which would be equal to the span of 2, 1. Okay. All right, so let's raise the difficulty here a little bit. We're going to have matrix B. We're going to raise the difficulty in one way, but we're also going to make it easier in another way. So matrix B is a 4x4 matrix, which certainly raises the appearance of difficulty. But as I get this matrix written out here, we'll see that as I look here, it is a triangular matrix, okay? And remember the rule for a triangular matrix. The rule for a triangular matrix is that the eigenvalues are simply the numbers on the diagonal, okay? So if I'm going to write the characteristic equation of this, b minus lambda I would have 5 minus lambda, 3 minus lambda, 5 minus lambda, and 1 minus lambda. And really, it doesn't matter what I have up here above the diagonal. Okay, they would be the same. They'd be the same things as we saw over here, but it doesn't matter what I have here because as I do this determinant, the only part of this determinant that's not 0 is going to be this main diagonal. All of the other diagonals, okay, are going to include zeros. You know, you can think about the cofactor expansion. You get the same type of ideas, right? If you ignore the row and column, I get all these zeros down here. Ignore the row and column, you get zeros. It'll cancel off all those reverses that you would subtract or all those ones you would add onto. Okay, so I have my setup there. That tells me that the characteristic equation is going to be 5 minus lambda, 3 minus lambda, 5 minus lambda, 1 minus lambda. Okay, and if I set that equals 0, I get that the eigenvalues are simply 3, 5, and 1. Now notice 5 actually appears twice here. Okay, so if it talks about the multiplicity of an eigenvalue, that's exactly like the multiplicity of a root of an equation. And ultimately, that's what we're doing here. We're doing the roots of polynomial equations, just like you might have done in a pre-calc class or an Algebra 2 class or a Calculus 1. We're doing the roots of those equations, okay? So the roots of those equations can appear more than once, which means they have a higher multiplicity. So if it tells you to write things out according to the multiplicities, then you need to have it appearing however many times it appears in the characteristic equation, okay? So the eigenvalues here are 1, 3, and 5. But the eigenvalues according to the multiplicities are 1, 3, 5, and 5. Okay, so if it says according to the multiplicities, you need to list it out as many times as it appears, okay? Well, we can also have a matrix, we'll call this C, has a characteristic equation. So rather than giving you the matrix here, I'm giving you the characteristic equation. Okay, the characteristic equation is going to be lambda to the 6th minus 9 lambda to the 5th plus 8 lambda to the 4th. Okay, and that's the characteristic equation. So I'm setting that equals 0 to find the eigenvalues. Okay, find the eigenvalues of C. Okay, well, as I look at this, all three of these terms have lambda to the 4th in common. So I'm going to factor out that lambda to the 4th. It's going to leave me with lambda squared minus 9 lambda plus 8 equals 0. Okay, continuing, I'm going to factor. So I get lambda and lambda again. Two numbers that multiply to a positive 8 but add up to a negative 9. So I need a negative and a negative. And then 8 and a 1 is going to add up to 9. And again, that's equal 0. So from this, I can say the eigenvalues are 1, 8, and 0. Okay? But if I need them according to the multiplicities, this is lambda to the 4th. So if it's lambda to the 4th, I'm going to actually have 0 4 times according to the multiplicities. Okay, so be mindful of that criteria. Okay. Okay, continuing. So one more example of this type, and then a definition we need to discuss. So I'm going to have a matrix A. This matrix A is equal to 1, 0, 3, 0, 3, 0, 0, 1, 2. Okay, so it's a 3 by 3 matrix. Now, there's some good news and some bad news here. The bad news is that it is not triangular. I have numbers that are above and below the diagonal. The good news is that there's a lot of zeros involved. So if I do A minus lambda I am going to subtract lambda on the diagonal. So 1 minus lambda, 3 minus lambda, 2 minus lambda. Then I have 0, 3, 0, 0, 0, and 1. Okay, so remember how you do determinants for a 3 by 3. So I'm going to do this one by a cofactor. So I take the first column here, because this column has 2 zeros in it. It's going to be the easiest to deal with. Okay, so my cofactor here, determinant A minus lambda I, going down the first column. So this is plus, minus, plus. So the first column, I get 1 minus lambda. Remember, ignore the row and column that it's in. So you get this matrix here. This is going to have 3 minus lambda, 0, 1, and 2 minus lambda. And we're taking the determinant of this in a second. But then I go down the column, so I'm going to get 0, and I don't really care what it's multiplied by because it's times 0. And I'm going to get plus 0, and again, I don't really care what it's multiplied by because it's going to be times 0. Okay, so we're doing good so far. I've got 1 minus lambda. Take the determinant here. It's going to be 3 minus lambda, 2 minus lambda, minus 0. So I have 1 minus lambda, 3 minus lambda, and 2 minus lambda. And again, we are setting this equal to 0 because it's a characteristic equation. So from there, I get that my eigenvalues are 1, 2, and 3. Okay? Now be careful of it trying to trip you up, right? 1 minus lambda is the factor of the characteristic equation. 1 is the eigenvalue, okay? So notice that that sign is switched, right? If I had lambda plus 1, the eigenvalue would be negative 1. So the factor and the eigenvalue relate, but they are flipped by that negative sign. Okay, so be mindful of that. Okay. All right, so let's keep going with B here and make, or with A, I should say, and make some other observations. So I've got A minus I. Okay, I'm subtracting 1 on the diagonal. Get my camera to cooperate here. So I'm subtracting 1 on the diagonal. I've got 0, 0, 3, 0, 2, 0, and 0, 1, 1. Okay, when you row reduce that, use your favorite method for row reducing. So you're going to get 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay, so x1 is my free variable, where x2 and x3 are both 0. So the vector then is 1, 0, 0. Okay, notice that this is the x-axis. This is the standard. This is identity vector E1. Okay, the span of it would give us the whole x-axis. That would be our eigenspace for that. Okay, A minus 2I. 1 minus 2 is going to be negative 1. 0 and 3 stay. 0, 1, and 0. 3 minus 1 is 1 there. 0, 1, and 0 for the last one, the last row. So I row reduce this. I'm going to get 1, 0, negative 3, 0, 1, 0, and all zeros in the bottom row. So I have then that x1 is equal to 3x3, x2 is equal 0, and x3 is a free variable. So the vector would be 3, 0, 1. And then the last one, A minus 3I. It's going to be negative 2, 0, 3, because I'll have 1 minus 3. 0, 0, 0 for the middle row. 0, 1, and negative 1 for the bottom row. When you row reduce that, you should get 1, 0, negative 1.5. 0, 1, negative 1, and then all zeros on the bottom row. So I have that x1 is equal to 1.5 x3, x2 is equal to x3, and x3 is a free variable. So my vector would be 1.5, 1, and 1. Or if you want to get rid of the fraction or the decimal there, multiply everybody by 2. You could also make that 1, 2, 2. Either of those would be acceptable eigenvectors to go with the eigenvalue lambda equals 3. Okay, so it's important when you're looking at the homework that you read the question carefully and make sure you understand what it's asking for. Okay, is it asking you for the vector? Is it asking you for the value? Is it asking you for a basis for the eigenspace, in which case you need all the vectors? Okay, and deduce those accordingly. All right, so we have one other definition that we need to cover in this section, and that's the idea of a similar matrix. Okay? So matrices are similar. Okay? A is similar. Notice that's not equivalent. Remember, we have a different definition for equivalent. Similar to B if there is an invertible matrix P such that P inverse AP is equal to B. Okay, we could also flip that around the other way. And we could write that A is equal to PB P inverse. Okay, we could write that in either fashion. Those are equivalent definitions, right? You can multiply by P on the left and start to get there, multiply by P inverse on the right and get there as well. And the reason that's important is that if I think about the determinants here, so if I take the determinant of both sides, then knowing what we know about determinants, I can split this determinant up. So I will have that the determinant of A is equal to the determinant of P times the determinant of B times the determinant of P inverse. And then I know these are just numbers. Determinants are just numbers. So I can write these in opposite orders. And I know that the determinant of P inverse is 1 over the determinant of P. Okay, we did that proof back. We talked about determinants. So this is just equal to the determinant of A times the determinant of B. So similar matrices have the same determinants, which will mean then that if I do A minus lambda I, that's going to be the same thing as B minus lambda I. Okay, so similar matrices have the same eigenvalues. Okay, and the same characteristic equation or characteristic polynomial. Okay, so similar matrices have the same eigenvalues and characteristic polynomial or characteristic equation. Okay, and this is actually theorem 4 for chapter 5. Okay, now it's important. I did not say row equivalent. Okay, row operations did not come anywhere in this definition. So remember, you cannot use row operations to determine eigenvalues. We actually do use them to find the eigenvectors. But you can't use them to find the eigenvalues. So you can't use them to find the characteristic polynomials. Okay, and just because this is a theorem in one direction, just because two matrices have the same eigenvalues doesn't mean they're similar. Okay, so it only goes one way. Similar matrices, same eigenvalues. If you have the same eigenvalues, you may not be similar. Okay, there's no reason to assume that would be the case. Okay, now that we've done this, we have a couple of new properties for our invertible matrix theorem. So remember back to our invertible matrix theorem, we wrote down all these things. We had a few more beyond this. Okay, we are now finally going to number this determinant of A not being 0. That's going to be letter T in our invertible matrix theorem. And we also have another, which is S. Okay, so I wrote them out of order here. But 0 is not an eigenvalue of A. Okay, so A is invertible when 0 is not an eigenvalue. If 0 is an eigenvalue, A is not invertible. Okay, so that's a couple of addendums to our invertible matrix theorem now that we know some additional information. Okay, so use a determinant of the A minus lambda I to find the characteristic polynomial, and then you solve that using algebraic methods. Okay, that's one way to find the eigenvalues. Okay, other ways, you use diagonal. You can go down the diagonal, things like that. Okay, so let's do one more example here that we need to talk about. Actually, I guess two more examples as I look carefully here. So I have a matrix A. This matrix A is 8, 2, 3, 3, 0, 2, H, 3, 0, 0, 8, 14, 0, 0, 0, 2. Okay? So clearly this is triangular. So lambda is equal to 2, 2, 8, and 8, subject to the multiplicities. Okay? Now, your multiplicity tells you that there could be 2 eigenvectors. Okay? It doesn't guarantee it, but there could be 2 eigenvectors. Because when I do a minus 8i, okay, so I'm going to use 8 here. I'm going to get 0 there. 2, 3, and 3 are untouched. 0, 2, h, and 3. Okay, the 2 got subtracted by 8, so it's now a minus 6. 0, 0, 0, and 14. And then 0, 0, 0, and 2. And so the question is, what values of h will give me a two-dimensional eigenspace? What values of h yield 2? So what values of h yield 2 eigenvectors for lambda equals 8? And we can do the same question here with lambda equals 2 as well. Okay. So let's take a look at our matrix here. I've got all zeros in the first column, so that sets up pretty decently. Okay. I want to get this, so this is going to be my first pivot. I want to get a 0 below it. Okay. So I'm going to do 3 times row 1 plus row 2 is going to replace row 2. So 0, 2, 3, 3 is untouched. 0, 0, okay, because 3 times 2 is 6. 6 minus 6 is 0. Okay, 3 times 3 is 9. 9 plus h is 9 plus h. And then this 3, it's going to be 12 now. 3 times 3 is 9, plus 3 is 12. This is 0, 0, 0, 14, 0, 0, 0, 2. Okay, now these bottom 2 rows are easy to take care of, so I'm going to drop below my question here. Bottom 2 rows are easy to take care of. 14 and 2, I could scale them both to 1, then they're the same. So my bottom 2 rows are going to be 0, 0, 0, 1, 0, 0, 0, 0 when I do those row operations. So let's go back to our top 2 rows. 9 plus h and 12. Okay, so right now I have 3 pivots. And if I have 3 pivots, I have 1 eigenvector. Okay, because I have a 4x4 system, so 3 pivots is going to give me 1 eigenvector. So the only way to get rid of this pivot is for 9 plus h to equal 0. Well, that happens when h is negative 9. So if h is negative 9, then my matrix here would look like 0, 2, 3, 3, 0, 0, 0, and 12, 0, 0, 0, and 1. Okay? To which I can see now I have x1 as a free variable, and I have x3 is a free variable. So there would be 2 eigenvectors. Okay? So let's write what those eigenvectors would be. So first, I could do scaling here. Divide this by 12, and then you put those rows together. So you're going to wind up with 0 there and just 1 above it. Okay? So continuing here, I know these are my free variables, so let's write the solution set. I'm going to write it here to the left. I'm going to have 2x1 minus 3x, sorry, 2x2 minus 3x3 minus 3x4. Nope, I got in a hurry. Sorry about that. So remember, we can go above this. I need to go to reduced row echelon form. So I'm going to do -3 row 2 plus row 1 is going to replace row 1. So my reduced matrix is actually going to be 0, 2, 3, 0, 0, 0, 0, 1. Okay, so I don't have that one there. That looks better. So I've got 2x2 minus 3x3. I've written that down incorrectly. Let me try that again. So I've got 2x2 is equal to minus 3x3, again, because we're moving that to the other side, okay? Sorry about that righto there. It's not really a typo because I'm not typing, okay? x3 then is a free variable. x1, remember, was a free variable. x4 now is equal to 0. So my eigenvectors, okay, for x1, that's going to be 1, 0, 0, 0. There are no other x1s in there. My other eigenvector is going to have 0. I've got 2x2 here, so I've really got negative 3 halves. Okay, x3 is the free variable, so that's 0, and x4 is 0. Okay, or you could write this as multiply everything by 2. I get 0, negative 3, 2, and 1. Okay, so my eigenvectors are this one or either of those two. Okay, but only when h equals negative 9. When h doesn't equal negative 9, I get 3 pivots. And when I get 3 pivots, x1 is going to be the only free variable. So this would be my only eigenvector, the 1, 0, 0, 0. Okay. All right, so I want to do one more similar to that, just to make sure we're on the same page. I know it could be a little confusing. I'm trying to give you plenty of examples. Please be in touch. If there's some way I can help you. Okay. So I'm going to have a matrix A. It's going to be 1, negative 3, 4, 0, 2, H, 0, 0, 1. Okay. So if lambda equals 1, what values or value of H will yield 2 eigenvectors? Okay, which we could also say is a 2-dimensional eigenspace. Okay, either thing. Okay, so I know I'm looking at lambda equals 1, so I want to do a minus I. A minus I is going to give me 0, negative 3, 4, 0, 1, H, 0, 0, 0. Okay. All right, so since I've got the 1 here, I'm actually just going to switch those two rows. Row 1 and row 2, I'm just going to switch because it's going to give me 1 in a more advantageous position. It'll make my row operations just a little bit easier. Okay, so now I'm going to do 3 row 1 plus row 2 is going to replace row 2. So I'm still going to have 0, 1, H on the top row. The middle row now is going to be 0, 0, and I get 3H plus 4. All zeros then on the bottom row. Okay, so this is a pivot no matter what. 3H plus 4, though, is only a pivot if it's not 0. And if I have 2 pivots, I have 1 eigenvector. 2 pivots would mean 1 eigenvector. But I could take 3H plus 4 and set it equal 0 and get 1 pivot. Okay, so if 3H plus 4 is equal 0, then I have that H is equal to negative 4/3. So I get a 2-dimensional eigenspace when H is equal to negative 4/3. Okay, and what that would mean is my matrix here would be 0, 1, negative 4/3, and 0, 0, 0, 0, 0, 0. And I could write a solution set. X1 is a free variable. X2 would be equal to 4/3 X3, and X3 would be a free variable, which would give me vectors 1, 0, 0, and then the other vector would be 0, 4/3, 1. And again, we might write this vector as 0, 4, multiply everything by 3 to get rid of the fraction. Okay, 0, 4, and 3. Because if x3 is 3, then I'm going to get 4/3 times 3 would be 4. Okay, so this is an eigenvector always. You could pick either one of these. You could actually pick any multiple. You could go up to 8, 6, 0, 8, 6 if you wanted to. Okay, so we need that position with h in it, that pivot position, or that possible pivot position, to be 0 in order to get that additional eigenvector in those setups. Okay, so characteristic equations, polynomials, similarities. I know we didn't do much with similarity at this point. We just kind of gave a definition, but it's going to play a big role in 5.3, which is about diagonalization. So we've talked a lot about triangular matrices. Now we're going to start looking at a diagonal matrix, which we haven't done as much with to this point. But diagonal matrices are very easy to work with. So that's the benefit of, if I can write a matrix in such a way that I can use a diagonal matrix, then that's going to make my work on that matrix a lot easier. Okay. If you have any questions, please, don't hesitate to contact me. I'm happy to help you, see what you need, what I can help with. I can give you materials. I can talk you through homework problems. Make sure you're staying up to date on those quizzes, tests, homeworks, etc. If you have any questions, please be in touch. Okay. Talk to you soon. We talk about 5.3 and diagonalization.